Okay, so it's my pleasure to introduce Dan Hathaway for today's talk. He got his PhD under Andreas Blas as the advisor, and then he had a postdoc with Natasha Dobrinin for a while. Now he's at the University of Vermont, and he's going to speak on a relative of ZF plus DC plus omega 1 is measurable.
Okay, well, thank you very much. So I'm not going to be looking at the chat, so if you have any question, just unmute yourself and ask me right away. Okay, so this is joint work with Francois Duray, who's also at the University of Vermont with me. So basically, we're going to look at a combinatorial statement which seems to be related to ZF plus DC plus omega 1 is measurable. Okay, so here's all the large cardinals that are related to what we're going to be talking about. So it really doesn't matter for this talk what the Mitchell order is, but let me define it anyway. So if you have normal ultrafilters U and W, we say that U is Mitchell below W if and only if U is in the ultra power of the universe using W. Okay, so the Mitchell order is an ordering on all normal ultrafilters on a measurable cardinal. It's a fact that the Mitchell order is always well-founded. The Mitchell order of a measurable cardinal is just the rank of this ordering. Okay, so here are the large cardinal theories from highest to lowest. ZF plus there's a measurable cardinal of Mitchell order kappa plus plus. That's the most you could have if you have GCH. And then below that, you have this weird thing, ZFC plus there is a cardinal with a weak repeat point. So I'm going to define that below. And that's stronger than ZFC plus there is a measurable cardinal of Mitchell order kappa plus. And then way below that, ZFC plus zero dagger exists. By the way, zero dagger is just a statement that there is an inner model with an there's an inner model with a measurable cardinal that has an elementary embedding into itself. And then that's stronger than ZFC plus a measurable cardinal. And then that's stronger than a ZFC plus an inaccessible cardinal. Okay, so the only really bizarre large cardinal axiom up here is a weak repeat point. So let me define it down here. Let kappa be a cardinal. U is a weak repeat point on kappa if and only if U is a normal ultrafilter on kappa, and for every set in the ultrafilter U, there is a normal ultrafilter W in the ultra power such that that set is in the normal ultrafilter. So none of the sets in the ultrafilter go away when you form these respective ultra powers. Okay, so anyway, it's just some strange large cardinal hypothesis whose strength is strictly in between Mitchell order kappa plus and kappa plus plus. All right, so getting started here. What exactly is the consistency strength of the theory ZF plus omega 1 is measurable? Well, Yek figured this out. So he showed that the following two theorems are equiconsistent. ZFC plus there's a measurable cardinal, and then ZF plus omega 1 is a measurable cardinal. So I guess the easy direction is not due to him. That's, Kunin and folks. So the easy direction is if you have ZF plus omega 1 is measurable, then in the L of mu model, the omega 1 of V is a measurable cardinal in the inner model, and it's an inner model of the axiom of choice. Okay, so ZF plus omega 1 is measurable implies there's an inner model of ZFC plus a measurable cardinal. The other direction uses, symmetric submodels. So Yek showed that if you have a model of ZFC plus a measurable cardinal, then there's an inner model of a forcing extension in which omega 1 is a measurable cardinal. And ZFC implies omega 1 is not measurable, so this model does not satisfy the axiom of choice. Okay, so ZF plus omega 1 is measurable is equiconsistent with ZFC plus a measurable cardinal, but something we're more interested in is what about when we add DC? So that's what the next slide is about. Okay, so what exactly is the consistency strength of ZF plus DC plus omega 1 is measurable? What do I say here? Let me just just note that AD plus V equals L of R implies ZF plus DC plus omega 1 is measurable. So AD just implies omega 1 is measurable, but AD plus V equals L of R implies DC. So anyway, just to get our bearings. At one point, people thought that a lot of the large cardinal strength of AD actually followed from ZF plus DC plus omega 1 is measurable. So let's see if that's the case. So in one direction, Mitchell showed that if ZF plus DC plus omega 1.
Excuse me, Dan.
Yep.
Dan, I think you're talking about with ZF plus DC plus omega 1 is measurable. I think you mean omega 1 is measurable via the club filter, because in the proof with YEC, if you just do the symmetric collapse, you're going to get ZF plus DC plus omega 1 is measurable. You're not going to have it measurable via the club filter, but I think that's what you mean here, is it not?
I think in his model, DC does not hold.
That is not true. In his model, DC does hold.
Yes, DC does hold in YEC's model. ZF plus DC plus omega 1 is measurable, is equiconsistent with a measurable cardinal. What you're talking about is ZF plus DC plus omega 1 is measurable via the club filter.
Okay. So I'll keep that in mind. So something I'm going to say later, let's come back to that point. Okay, so when I say ZF plus DC plus omega 1 is measurable, let's just assume I mean ZF plus DC plus omega 1 is measurable via the club filter. Okay. So ZF plus DC plus omega 1 is measurable via the club filter. So Mitchell showed that this implies there's an intermodel with a weak repeat point. Okay, so the strength of this is at least a weak repeat point. So what that shows is ZF plus DC plus omega 1 is measurable via the club filter. That is strictly stronger than ZF plus omega 1 is measurable. What about the upper bound? Well, so Radin had a forcing, and then Wooden had an iteration technique. And if you combine these two, you could start with a very large cardinal and then get a model of ZS plus DC plus omega 1 is measurable via the club filter. And then Mitchell looked at this result and improved the upper bound to a Mitchell order of kappa plus plus. And then finally, in 2007, Mitchell significantly lowered the upper bound. So Mitchell lowered the upper bound all the way to ZFC plus there exists a weak repeat point. Okay, so in other words, the consistency strength of ZFC plus DC plus omega 1 is measurable via the club filter is exactly ZFC plus there exists a weak repeat point.
I think Mitchell's 2007 is just a preprint, and it still has some gaps.
Okay.
At least that's what's on archive.
Yeah, so I mean, I don't think it's been published, you're right, but just according to the archive, that's what he's claiming. Yeah. Okay. So this is just a summary of the two things I said, but keep in mind with the comment people made that by here I mean ZF plus DC plus omega 1 is measurable via the club filter. Okay. So ZF plus omega 1 is measurable is equiconsistent with the measurable cardinal, but once you add DC and omega 1 is measurable via the club filter, the consistency strength jumps way up to a weak repeat point. Okay, so this slide, I think maybe we could have a discussion about. So I claim that each item implies the next, and the bottom item plus DC implies the top item. So in particular, this would give ZF plus DC plus omega 1 is measurable is the same thing as ZF plus DC plus omega 1 is measurable via the club filter. And it sounds like people think that's not the case. So I mean, if we go through this, 1 implies 2, 2 implies 3, 3 implies 4. Those are all easy implications. The only non-trivial one is 4 plus DC implies number 1. So let me go through this theorem, and we could talk about it if necessary. So 1 implies 2. So number 1 says every real has a sharp, and every subset of omega 1 is constructible from a real. So that implies that the club filter on omega 1 is an ultrafilter. Why is this? Because if you have an arbitrary subset of omega 1, you can fix a real that constructs that set, and then a final segment of L bracket R indiscernibles below omega 1 are either in A or not in A. So A either contains a club or is disjoint from one. So I don't think we should have any issue with that. 2 implies 3. All I'm saying in 2 implies 3 is the club filter on omega 1 is an ultrafilter if and only if the club filter on omega 1 is a normal ultrafilter. And my proof for that, right, is to look at regressive functions. Suppose you have a subset of omega 1 that contains a club, and let f from x to omega 1 be regressive. Then by Fedor's lemma, f is constant on a stationary set y. Now, since we're assuming number 2, then we have that y either contains a club or is disjoint from a club. But if y is disjoint from a club, then we have a stationary set disjoint from a club, which is impossible. So y must contain a club.
Fodor's lemma is not provable from ZF. You need to have a more refined argument.
Okay. So maybe this is where there's a problem.
Mm-hmm.
I had to think about that. Okay. All right, and then
in fact, there was an old result which is not really valid. In fact, this was claimed many years ago, about 40 years ago, by Mitchell Spector, that you could force over L in order to get the club filter on omega 1 to be an ultrafilter. Now, Magidor, about 10 years ago, found a flaw in Mitchell Spector's proof. It was due to Mitchell Spector. And Asaf found just blew the doors open on it. The proof was just completely false. But on the face of it, just thinking that the club filter on omega 1 is an ultrafilter, there's no reason to think that that couldn't be forced over L. The proof that was claimed for that is invalid, but there's no reason to think that the proof could not somehow be modified so that you could force over L to get the club filter on omega 1 as an ultrafilter. In fact, when Mitchell Spector had claimed this, I remember a discussion at this old set theory seminar called NEST's Northeast Set Theory Seminar, which hasn't run since 1994, but Baumgartner used to attend this seminar, and Baumgartner, in fact, referenced this about Mitchell Spector having made this observation that you can force over L and get the club filter on omega 1 to be an ultrafilter. So prima facie, there is nothing which says that the club filter on omega 1 being an ultrafilter is stronger than CONZF. Prima facie, you might be able to force this over L. It was claimed, but the proof is just completely false. But there's nothing outright that says that it couldn't be done.
Okay, so maybe the club filter on omega 1 being an ultrafilter is equiconsistent with ZFC. So even if we get rid of number 2, however, I do think that 1 implies 3.
So just Arthur, a small remark on what you said. There's no DC in the proposed model of Spector. I think that with DC you can, in fact, salvage this 2 to 3.
Okay, no, that's right. I'm sorry, I should have said that, Asaf. 100% correct. Spector's proof would not have gotten DC. AC omega would have failed completely. That's right.
Right. So I can make the weaker claim that if you add DC to all 4 of these things, then they're equivalent.
Well, again, except the 4th one.
Except 4 implies 1.
Well, the 4th is just weaker. We know that because, the.
No, but I mean, if I add DC to 1, 2, 3, 4.
Yeah, but in the YAC model, you have ZF, DC, omega 1 is measurable.
Okay.
And that's weaker than the club filter. That was the remark at the start by Arthur and myself.
Right.
Okay.
Right. Omega 1 is measurable plus DC. That's just there's a measurable cardinal. That's all there is to it. The symmetric collapse is going to give DC.
Okay. All right. All right. So I'm going to take a step back here, and I'm not claiming this theorem, but there's only one of these things that I'm really going to use later, which is every real has a sharp, and every subset of omega 1 is constructible from a real. And this should follow from DC plus the club filter on omega 1 is a normal ultrafilter. So that's really the only direction which I'm going to use later. So there is a mistake here, I guess. Yeah. And let me talk about the omega 1 is measurable cardinal implies number 1. So we're going to say let's say omega 1 is a measurable cardinal as witnessed by a normal ultrafilter. Then that is discussed in a paper by Philip Welch in 1994, where he talks about subsets of omega 1 being constructible from a real. Okay, so there's a lot of problems with this, it sounds like, but I really only care about number 1. Every real is constructible. Every real has a sharp, and every subset of omega 1 is constructible from a real. Okay, here's the combinatorial statement that I want to look at. So I'm calling this phi. So let phi be the following statement. For any function f from omega 1 cross omega 1 to omega, there are functions g1 and g2 from omega 1 to omega, such that for all x and y in omega 1, f of x, y is less than or equal to the max of g1 and g2. Okay, what's going on with this statement? So phi says if you have any matrix of natural numbers, which is omega 1 by omega 1, then there's a length omega 1 row vector and a length omega 1 column vector, such that each entry of the matrix is less than or equal to the maximum of the entries in the row and column vector. Okay, any questions about what this phi is saying? All right, so the claim I'm going to make in the rest of this presentation is that if you combine phi with fragments of the axiom of choice, you're going to get stronger and stronger theories. So first, you can show that phi is actually inconsistent with so phi is inconsistent with the axiom of choice. So the result here is if omega 1 is regular and there is an injection of omega 1 into R, then phi is false. So what that tells you is that if omega 1 is regular and phi happens to be true, then there is no injection of omega 1 into R, and that gives you some small, large cardinal strength. Because if there's no injection of omega 1 into R and omega 1 is regular, then in any model of the axiom of choice, the omega 1 of V is inaccessible in that model. Okay, the intuition we want to have about the statement is phi implies that omega 1 behaves like omega, but in a way that is inconsistent from the axiom of choice. Now, just phi by itself could be equiconsistent with ZFC. We don't know that, but we do have examples of where when you add more and more fragments to the axiom of choice, you get stronger and stronger theories. And of course, if you add axiom of choice itself, you get 0 is equal to 1.
Sorry, can you just say what you mean about that omega 1 behaves like omega? How is this saying that?
Well, so if you look at this definition of phi, if you replace omega 1 with omega, it's true. Because if you have a matrix which is omega by omega of natural numbers, then you could have a column vector that eventually dominates all the columns of the matrix, and then your row vector could pick out values to make the whole thing work.
Oh, I see. Yes. Okay.
Yeah. So yeah. So phi, the way I think of it is phi implies omega 1 behaves like omega in a way that's inconsistent with the axiom of choice. Okay, this is kind of information overload. I'm going to take back the statement. So what this theorem should say is if every real has a sharp and every subset of omega 1 is constructible from a real, then phi holds. That's what this argument is really saying. And the reason for this is to show phi, you want to start with an arbitrary function f. Well, f is essentially a subset of omega 1. Therefore, it's constructible from some real little r. And then because R sharp exists, you can analyze L bracket little r using indiscernibles. and these indiscernibles end up showing that F has a lot of symmetry. And you can exploit this symmetry to create the functions G1 and G2. Okay, so that's all I'm saying in this argument. The fact that I'm saying ZF plus DC plus omega 1 is measurable here just came from that theorem, which, you know, maybe it's not right now, that says that implies every real has a sharp and every subset of omega 1 is constructible from a real. The point I'm making on this slide is, even if you just have the axiom of determinacy, you still have that every real has a sharp, and you have that every subset of omega 1 is constructible from a real. So and that means that ZF plus AD implies phi as well. And what I'm conjecturing here is that, you know, if you take DC some weak theory, you should actually be able to get that omega 1 is measurable. Okay, the point I'm making here is if we want to get lower bounds for phi, it seems difficult, but if we combine phi with fragments of the axiom of choice, then we can actually get some large cardinal lower bounds. So like I said before, ZF plus phi could be equiconsistent with ZFC. That's certainly possible. On the other hand, ZF plus phi plus omega 1 is regular implies that the omega 1 of V is strongly inaccessible in any inner model of ZFC. And that's by an argument I mentioned before, which is if you have phi and omega 1 is regular, it must be that there's no injection of omega 1 into R. And then if there's no injection of omega 1 into R and omega 1 is regular, then you get this result: omega 1 of V is strongly inaccessible in any inner model of ZFC. Okay.
Sorry. Before you move along, can I ask? I don't really have experience with, you know, choiceless principles and so on, but I wonder, is phi somehow a fragment or something? Is it implied by some, you know, well-known principle that you know lives somewhere? Like I'm trying to find sort of motivation for phi. Like, what is the I know you said some intuition that omega 1 behaves like omega, but I wonder if it's sort of rooted somewhere else also.
Well, that's a good, I don't really know. I mean, it's some kind of strange combinatorial statement that is a consequence of AD. And I'm trying to figure out, in the landscape of AD with all the statements, I'm trying to figure out exactly how strong it is and what it implies. I mean, we're going to see shortly that phi is basically giving you some kind of failure of covering. I mean, if you take phi and combine it with fraction of the axiom of choice. But I don't have a really good answer of like, what is another combinatorial statement that is very similar to phi? Okay, so that's all I'm going to say about phi by itself, and that's also all I'm going to say about phi plus omega 1 is regular. However, we can say a lot more if we look at the theory phi plus the club filter on omega 1 is normal. Right? So we're not saying that the club filter is a normal ultrafilter, we're just saying that the club filter on omega 1 is normal. All right, so how are we going to get any kind of large cardinal strength from phi plus the club filter on omega 1 is normal? So our strategy is going to be to use this thing we're calling the black box. So the black box is the following statement: for any inner model M of ZFC, the omega 1 of V is strongly inaccessible in M, and there's a club subset of the omega 1 of V of regular cardinals of M. Okay, so it's kind of unusual to have a club subset of omega 1, all of whose elements are regular cardinals of M, right? Because I mean, if you think about just the omega element of C, it's going to have cofinality omega in V. On the other hand, it's going to be a regular cardinal of M. All right, and something else to note about this whole scenario is, you know, if you have an inner model M of ZFC, and you use the black box to get this club C, then the model M bracket C will also satisfy the axiom of choice. This is because whenever you have an inner model of the axiom of choice and adjoin a set of ordinals, the resulting model will still satisfy choice. So in M bracket C, omega 1 of V will be inaccessible in M bracket C. And so we can find arbitrarily large singular cardinals of M bracket C that are regular cardinals of M. So the black box, you know, applied to any inner model of ZFC M will give this outer model of M where there's lots of singular cardinals that are regular in M. And our question is, what exactly is the large cardinal strength of the black box? So let's talk about an upper bound first. So doing a little bit of work, you can show that ZF plus phi plus the club filter on omega 1 is normal actually implies the black box. Okay, so what that tells you is the consistency strength of the black box is upper bounded by ZFC plus a weak repeat point. And a lower bound for the black box, what is it you know, is it equiconsistent with a weak repeat point? We don't know that exactly, but that's what we're going to talk about now.
Sorry, do you know that you need phi? Do you know whether or not just assuming that omega 1, the club filter on omega 1 is normal implies the black box or not?
Well, no, because ZFC implies the club filter on omega 1 is normal. But ZFC
sorry, for some reason I was reading that as ultra filter. Never mind. Excuse me.
Oh yeah, right. Yeah. So our axiom of choice assumption is just the club filter on omega 1 is normal. So we're not making any kind of statement that omega 1 is measurable via the club filter.
Okay. Sorry. Yeah. Thank you.
Yeah. So let me just say something about when an inner model is wrong about a cardinal being a singular. So we say that an inner model M is correct about the singulars of V if and only if every singular cardinal of V is a singular cardinal of M. And being correct about singulars is upward absolute. So if M1 is an inner model of M2 is an inner model of V, then if M1 is correct about singulars, then so is M2. And this bottom comment I'm making is that if you have an inner model which is wrong about singulars, and it's wrong cofinally below some lambda, and then you force over this inner model by a forcing less than lambda, then the resulting forcing extension is also going to be wrong about singulars. Okay, so if you're wrong about singulars, generally your forcing extensions will also be wrong about singulars, provided you know you're doing a forcing less than some cardinal and the inner model is wrong about singulars cofinally below lambda. Okay, so how are we going to get a large cardinal strength from the black box? So here's one way. So suppose we have a large LC is a large cardinal axiom, and K bar is definable inner model such that in any model N in which its K bar is not correct about the singulars of N, then N has an inner model satisfying the large cardinal. So let me say that one more time. So, I mean, often you have the situation where there's a large cardinal axiom and a definable inner model such that if the definable inner model is not correct about singulars, then there is an inner model with that large cardinal axiom. So this happens, for example, with an inner model with a measurable cardinal and the Dodd-Jensen core model. So how exactly can we use, you know, this phenomenon with the black box? So assume the black box. We can try to create an inner model M of ZFC and this club subset of omega 1 coming from the black box such that the K bar of M bracket C will be contained in M. Okay, so we want the K bar of M bracket C to be contained in M. Why would we want this? Well, because the black box gives us that M is not correct about the singulars of M bracket C, it must also be true that the K bar of M bracket C is not correct about the singulars of M bracket C. All right, so M bracket C thinks that K bar is not correct about singulars. Therefore, M bracket C has an inner model satisfying the large cardinal axiom. And therefore, V has an inner model with the large cardinal axiom as well. Okay, any questions about what I mean by this mining technique? All right, so let's just see, you know, a specific example of how this is used. So Dodd and Jensen showed that the definable KDJ is not correct about singulars, then there is an inner model with a measurable cardinal. Okay, so so we can use that with the black box. So the black box implies there's an inner model with a measurable. So how are we supposed to do this? So the whole tricky part is coming up with the correct M, but let's let M be the Dodge-Jensen core model, and let C be a club subset of omega 1 coming from the black box. Now, here's something about the Dodge-Jensen core model. The Dodge-Jensen core model of M bracket C is actually the Dodge-Jensen core model. All right, now, since M is not correct about the singulars of M bracket C, then therefore the Dodge-Jensen core model of M bracket C is not correct about the singulars of M bracket C. So in other words, M bracket C thinks its Dodge-Jensen core model is wrong about singulars, therefore it thinks there's an inner model with a measurable cardinal. Okay, so there you go. The black box implies that, I mean, black box gives you this kind of failure of covering, so it makes sense that you can get inner models with large cardinals from this. I want to make this small comment here that, you know, in M bracket C, we had an inner model with a measurable cardinal. I claim with just slightly more work, you could get an L of mu model whose measurable cardinal is strictly less than the omega 1 of V. Okay, so the black box, so the black box and therefore phi plus club filter on omega 1 is normal implies an inner model with a measurable. The comment on this slide is that the black box implies that zero dagger exists. So this is a similar kind of covering scenario. So assume there's an inner model with a measurable. Take the unique such L of mu model whose measurable kappa is smallest. Then if zero dagger does not exist, then either L of mu is correct about the singulars of V, or there is a G that is prickly generic over U, prickly generic for U over L of mu, such that L of mu bracket C is correct about the singulars. All right, so what I'm saying is, if there is an inner model with a measurable, but zero dagger doesn't exist, then this L of mu model or a forcing extension of it will be correct about singulars. So using a similar argument as before, we can get that the black box implies zero dagger exists. So the main trick is which M to use. So we're gonna let M be the L of mu model with the smallest measurable cardinal kappa. And on the last slide, we said that kappa is smaller than omega 1. And let C subset of omega 1 come from the black box. Now M is still the L of mu model of M bracket C with the smallest measurable cardinal. So, you know, we do some little absoluteness argument there. Now M is not correct about the singular cardinals of M bracket C. I mean, that just comes from the definition of C from the black box. And not only is M not correct about the singulars, if you do any prickly forcing extension of M using a poset of size less than omega 1, that forcing extension is also not going to be correct about singulars. And therefore M bracket C thinks that zero dagger exists. And then with some argument, because M bracket C thinks zero dagger exists, it must be that zero dagger exists. Okay, any questions about that? All right, so we saw one mining technique, which is, you know, if a certain definable inner model is not correct about singulars, then there's an inner model with a large cardinal. So this is going to be a slightly different technique. So we're going to want to assume an anti-large cardinal hypothesis. And we're going to get that the black box implies there are large cardinals in the core model. So instead of getting any old inner model with a large cardinal, we're going to get the large cardinals inside the core model itself. All right, so this next theorem is, in this form, is due to Sean Cox. It says, assume there's no sharp for a strong cardinal, so there's no mouse with an overlapping extender. Let K be the core model. Assume kappa is singular in V but regular in the core model. And also assume that kappa has uncountable cofinality, nu. Then the core model thinks that kappa is measurable with Mitchell order, at least nu. All right, so let me say this one more time. As long as you're assuming this anti-large cardinal hypothesis, if the core model is wrong about a cardinal being singular, and if the cardinal has high cofinality in V, then the cardinal will have high Mitchell order in the core model. So one other thing we have, remember from before we said any inner model which contains the Dodge-Jensen core model is correct about the Dodge-Jensen core model. I'm not sure if the same is true with these larger core models, but we do have the following. So assume that there's no inner model with a wooden cardinal, let K be the core model, and then let N be an inner model, then the core model of N is contained in the actual core model. So as long as there's no inner model with a wooden cardinal, whenever you're looking at an inner model, the core model of that inner model is contained in the actual core model. So the core model never sticks out when you restrict to an inner model. How do we need that in terms of our black box argument? Well, if there's no inner model with a wooden, and if we let M be the core model, then the core model of M bracket C is going to be contained in M. Right, because the core model of M bracket C is contained in K, which is equal to M. So here's how we can use that second mining technique for the black box. So let kappa be less than the true omega 1. I claim that the black box implies there's an inner model M with a measurable cardinal gamma of Mitchell order greater than or equal to kappa. All right, so one thing that differentiates this from the previous theorems is that here we need an anti-large cardinal hypothesis in order to say the right thing about the core model. So we're going to assume without loss generality that there's no inner model with a measurable lambda of Mitchell order lambda plus plus. And it's okay to do that without loss generality, because if there was such an inner model, then somehow we could get an inner model, you know, with a cardinal of large enough Mitchell order. Okay, so assuming this anti-large cardinal hypothesis, we get two things. We've got every inner model thinks there's no inner model with a wooden, so we can use one of the things from the previous slide. And also, there's no sharp for a strong cardinal. Then we're going to let M be the core model. And we're going to let C subset of omega 1 be a club that comes from the black box. So what the black box gives us is a cardinal gamma, which is singular in M bracket C, but you know, that is regular in M. And we can pick the singular cardinal to have arbitrarily large cofinality. So we're going to pick the singular cardinal of M bracket C to have cofinality at least kappa. Sorry, I should have said at least kappa there. Okay, so kappa is less than gamma less than omega 1 of V. This should be a period, sorry. All right, so since this gamma is in C, it's regular in M. So what we have here is that gamma is regular in the core model of M bracket C. Remember, the core model of M bracket C is contained in M. So since gamma is regular in M, also gamma is regular in the core model of M bracket C. Okay, and therefore, by Cox's result, M bracket C thinks the core model has this measurable of Mitchell order at least kappa. Okay, so that's just an example of using this second mining technique. But this is as far as we got. This is the largest large cardinal hypothesis we know is a lower bound for the black box. So I'm just going to end with some open questions. So first, I'm just wondering I mean, phi is some strange combinatorial statement, but if you just combine it with something, does that actually give you omega 1 is measurable, or even omega 1 is measurable via the club filter? Okay, so this first question, I'm saying combinatorially, what is the status of phi? My second question is, what is the consistency strength of the black box? So we know an upper bound for the black box is a weak repeat point. This is because, you know, the black box follows from phi plus club filter is normal, and that follows from a weak repeat point. And we also know that the black box has these lower bounds of measurables of high Mitchell order, but we don't know if the black box implies there's an inner model with a measurable kappa of Mitchell order kappa. So that's the first large cardinal we don't know is a lower bound for this. And my third question is, what happens when we take phi and replace omega 1 with omega 2? So if you go at the definition of phi and just replace all instances of omega 1 with omega 2, you get some statement that seems very hard to believe. We don't know anything about it. We don't know if it's inconsistent. We don't have any kind of upper bound for it. So, you know, for you guys that like, for choiceless combinatorial questions, I'd recommend taking a look at that and seeing, can you get any kind of upper bound for that statement? And that's it. So I want to thank Andreas Bloss, Cody Dance, and Trevor Wilson for talking about some of this work. Okay, that's it.
Thank you very much, Dan. It was a great talk.
Yeah, yeah, there were some mistakes. You guys pointed out some subtle mistakes I was making. I think the big problem I had was I just assumed Fedora's lemma was a ZF theorem.
Right.
Yeah,
but I mean that's the value of giving a talk to a knowledgeable audience. So are there any questions or comments?
I have a question way back at the beginning because I don't know anything about these weak repeat points.
Okay.
You had them sandwiched between Mitchell order kappa plus and Mitchell order kappa double plus. And there are a few more ordinals between kappa plus and kappa double plus. Is anything known about connection between repeat P points and any of those ordinals as Mitchell order?
I have no idea. I would think it would be Mitchell order, some ordinal which is highly non-canonical, which you can't describe. But I don't. But maybe it's like maybe it's kappa plus times 2. I don't know. I would suspect not, but I don't know.
Okay, thank you.
Yeah.
Any further questions?
I have a question.
Okay.
Is it? I can't remember, but doesn't Martin's axiom somehow related to like eventual domination? I can't remember.
Well, it implies that all the cardinal characteristics are equal to C.
Does this have anything to do with, like, does phi have anything to do with like another version of Martin's axiom or something like that?
Well, so here's something. Suppose you look at phi, but instead of an omega 1 by omega 1 array, you have an omega by lambda array. Then in ZFC, phi is true. This phi statement is true if and only if lambda is less than the bounding number. So if you have an omega by continuum, you can have an omega by continuum array in ZFC, which shows that this phi is false. But anything strictly smaller than the bounding number. So Martin's axiom would tell you a little bit about when phi fails, when this version of phi fails.
Okay. Yeah. Think about it. Thank you.
Yeah.
At the risk of going off on a tangent to a tangent, I was somewhat surprised by what Arthur was telling us about Mitchell-Spector's result, where the proof turned out to be wrong, but the result might actually be revivable. If you had a situation like that where the club filter on omega 1 is an ultra filter, but you've got basically no consistency strength there, I assume that means that club filter, although it's ultra, is not countably complete. Even though the intersection of countably many clubs is a club, the intersection of countably many supersets of clubs need not be a superset of a club. Is that what's going on, or is that part of what's going on here? Or am
I don't think that's a ZF theorem.
No, so that is actually quite possible without any large cardinals. You can have all club alter filters not even sigma complete. So that there's no large cardinal strength to that at all, regardless being alter filter or not. But definitely, if you don't have choice, not even countable choice, and the club filter is an alter filter, it will, if you fail to have DC, if you fail to have large cardinal strength, it will certainly not be countably complete. You cannot choose the clubs. That's the whole point.
Thank you.
I will also add that with Yair Hayut, after Arthur set me on this problem 5 years ago, so with Yair Hayut, we've been trying to work on this every now and then, and we try to come up with creative new approaches, but none of them stick so far, not even with mild large cardinal hypothesis. So contrary to what Arthur said, I'm not so sure that this statement is just a ZFC equivalent.
Well, prima facie, it doesn't seem to have a large cardinal strength. That's what I'm saying. Now, maybe you can get some kind of large cardinal strength from it, but just on the face of it, it looks as though you might be able to force it over L. I think it would be very, very interesting if you could show that the club filter on omega 1 is an ultra filter, even without AC omega holding. If you can get some large cardinal strength from that, I think that'd be absolutely fantastic. That would be a good theorem to prove.
Yeah.
Okay, any further questions or comments? Tangents?
So I'm remembering some paper of Dan's from a couple years ago, and I think you had some sort of related notion to this phi that had to do with Tukey on functions on, was it omega 1, I think? Anyway, I was wondering if this phi was related to that result.
Yeah, I don't think it's related to that.
Not at all. Okay.
I think, but I gave a talk about this thing a long time ago. So maybe it was the same thing. Yeah. But I'm not, yeah.
Okay, any more questions? Well, if not, then let's thank Dan again.
All right, thank you all.
Thanks a lot for the great talk.
Thanks.
Okay, I'll stop recording.